Okay, so in the first video lecture for today, we discussed the slide, what does the value of K mean? Remember, K equals products over reactants. So K, I want you to always think about products over reactants raised to the coefficients. So if K is really, really big, that means we have mostly products, or products predominate. If K is really, really small, that means that number downstairs, which stands for your reactant concentrations, is much larger, and your reactions are dominant. So that was our last video lecture. Now we're moving forward, and we're going to start with practice exercise 3. So it says for the reaction, H2 gas plus I2 gas, again, this means in equilibrium with 2HI gas. So equilibrium, the forward rate equals the reverse rate. We're given Kp equals 794 at 298 K, and Kp equals 54 at 700 K. So remember, capital K is your equilibrium constant. P stands for partial pressure, so your concentration of the gases would be in units of atmospheres. And the question says, is the formation of HI favored more at higher temperatures or lower temperatures? So what that means, when do we have more HI, at high temperatures or low temperatures? So what I want you to think about is HI a product or reactant? We see HI as a product, so what does that tell us? If we want more product, do we want a larger K or a smaller K? And then which temperature is it favored? So please go ahead, pause the video, think about this question, rewind and listen to my introduction of this exercise again, and then go ahead, once you write down the answer, hit play and check your work. Okay, so pause now. Okay, so I assume you've all paused, you wrote down an answer, let's go ahead and look through it together. So remember, larger K equals products are favored, and HI is indeed a product in this reaction. At 298 K, so at our lower temperature, Kp equals 794, while at 700 K, so a higher temperature, Kp is smaller. So again, we said the larger K products are favored, and this is indeed our larger K. So what temperature is that? That it corresponds to our lower temperature. So therefore, products are favored at the lower temperature, which is indeed 298 K. Okay, moving on. Manipulating equilibrium constants. So I think I have this animated, yeah. Okay, so let's think about this. What happens if I rearrange a reaction? How does that affect K? So we'll start with this reaction, dinitrogen tetroxide gas in equilibrium with 2 nitrogen dioxide gas. What would K be? So go ahead, pause, write down K, then hit unpause and come back. Okay, so thank you for doing that. Let's go ahead and see. So K, again, Kc, so what does that mean? Are we putting in units of concentration in terms of molarity or partial pressure? Gases, obviously we could do either one, molarity or partial pressure, but Kc tells us we put in units of molarity, so we represent that with square brackets, and we have the concentration, again, products raised to their coefficient, so NO2 squared divided by N2O4, and that equals 0.212. So this number is given to us. I'm telling you all, this is the number for K. And this is our K expression based on this reaction. So if I reverse a reaction, so if just go ahead, I reverse the reaction, my products become my reactants, my reactant becomes a products, what is our K going to be in this case? So pause, write this down, unpause, come back. Okay, so again, Kc, we're looking for molarity, so we represent that in square brackets. So what have we done? Now we have N2O4 divided by NO2 squared. So that equals 4.72. How did we go from 0.212 to 0.472? How are those two numbers related? Well, how are these two reactions related? These two expressions. what do we do to go from the first to the second K expression? We just flipped it over, took the inverse. So we took the inverse, that means, and I want you to double check this on your calculator so you believe me, 1 divided by 0.212 does in fact equal 4.72. So what does that mean? If I reverse a reaction, I take the inverse of the K value. So this is just 1 over K C1. So I'll call this KC1 and this KC2. So now let's go ahead. Again, summary, you reverse a reaction, you take 1 over the K value. Now again, the same KC1 reaction. What did I do? I went from N2O4 to 2N2O4. I went from 2NO2 to 4NO2. And again, our KC expression, products over reactants. So NO2 squared over N2O4, the same as our first reaction. We're just now going to multiply a reaction by 2. Right, so you multiply this entire reaction times 2. And now what happens to the K expression? Now we end up with, again, pause, write it down. Okay, so thank you for pausing and writing that down on your own. Now you can check your work. KC is going to be, products, so NO2 raised to the coefficient of 4, divided by reactants, N2O4 raised to the coefficient of 2. So that equals our K value squared. Because what did I do to go from here to here? I just took K C1, KC1, and I squared it. So in summary, if you reverse a reaction, you take 1 over the K value. If I multiply a reaction by 2, I square the K value, both the expression and the numerical value. Okay, so let's go ahead and now we can look at practice exercise 4 for the formation of NH3 from N2 and H2, so the production of ammonia gas from elemental nitrogen and hydrogen gas. Kp is 4.34 times 10 to the negative third at 300 degrees Celsius. What is the value of Kp for the reverse reaction? So remember, if you reverse a reaction, think about it. What do you do to K? Look at the notes you just wrote down, pause this video, and then come back and we'll check our work together. Okay, so pause now. Okay, so thank you for pausing, and now we'll look at this reaction together. Again, essentially, we're given a reaction. They ask for Kp for the reverse reaction. So again, Kp just means the expression you'll be putting in the units of atmospheres for the gases. So for the reverse reaction, if I reverse the reaction, remember you take the inverse of the K value. It doesn't matter if it's Kp or Kc. So Kp for the reverse reaction is then 1 divided by 4.34 e negative 3, which equals 230. And that dot is really just a lazy way of saying this is 3 significant figures. If I don't include the decimal, that 0 is ambiguous. You could have also written 2.30 times 10 to the positive 2. So again, reverse the reaction, inverse, make sure you get this number in your calculator. Okay, practice exercise 5. Given that at 700 Kelvin, Kp equals 54.0 for this reaction, hydrogen gas plus iodine gas is in equilibrium with 2Hi, and Kp equals 1.04 times 10 to the negative fourth for the reaction N2 gas plus 3H2 gas in equilibrium with 2NH3 gas. Determine the value of Kp for the reaction 2 ammonia plus 3I2 in equilibrium with 6Hi plus N2 gas at 700 K. Okay, so again, what's happening? we're given this reaction and the corresponding Kp value. We're given this reaction and the corresponding Kp value. And then you're asked to get the Kp for this new reaction. So this, we will use the problem-solving skills we learned in Chem 101 for Hess's law. Remember, if you add two reactions with Hess's law and you want to get a new delta H value, you can add the values of delta H. So what we're going to see, if you can add two reactions and you know the K values, you can solve for the new K value of the target reaction by multiplying the Ks. So if you remember Hess's law from Chem 101, I want you to go ahead and listen to a couple tips I have, and then you'll pause the video when I tell you. So when I'm solving this problem, I'm thinking with my two given reactions, again, given 1 and given 2, I need to figure out how can I manipulate these reactions so that when I add them together, I get result with the target reaction. The target reaction is a reaction that we need to find the K value for. So I look for what I call unique species. A unique species is a reactant or product that only appears in one of the two given reactions and also appears in the target reaction. So for example, what is not unique? H2. H2 is not unique because it's present in reaction 1 and present in reaction 2. What is unique? Ammonia. So I see I have two ammonia on the right in the given, but in the target I need it on the left. So think, how do I get my product and turn it into the reactant? Again, how do I take a product, manipulate this reaction so it becomes a reactant? Well, remember our options based on manipulating K from the previous slide. You can either multiply a reaction by a coefficient or you could divide. So if you divided everything by 2, you would just take your K value to the 1/2 power. Or we can reverse a reaction, and if you reverse a reaction, K is 1 over the initial K value. So if you remember Hess's law, go ahead and pause this video, work on this problem, try and solve it, unpause, we'll go over it together. Okay, so thank you for pausing and giving this problem a shot. Let's go ahead and look at it together. So again, my given reactions are the reactions that are provided and have a corresponding K value. The target reaction is the reaction that you're trying to get as the answer when you add the two given reactions together. The target reaction is the reaction that you're generally trying to solve for that numerical K value. So what are we looking for? Unique species. Again, a reactant or product that is only in one of the two given reactions. Oops, let's see. My animations are a bit off. Hopefully they get better. Okay, so here is one of my given reactions. Again, a unique species, NH3. I have NH3 on the right, but in the target, I want it on the left. So what do? I reverse my reaction. If I reverse my reaction, what's going to happen to my K value? Correct. We take 1 over the initial K value. So now Kp for this new rearranged reaction is 1 over 1.04 10 to the -4th, which was given in the problem. Right, this is the reaction. I reverse it. My new K is 1 over this value. And now I have my NH3 done. So oftentimes I like to circle these reactants or products. So I know my 2 NH3 is taken care of. That's supposed to be circled, not crossed out. Whereas another unique species, well, my H2, remember we talked about, is not unique, and this line is ahead of where it should be. We'll talk about that in a minute, but I can see in my target reaction what is another unique species, my HI. My given reaction, I have 2 moles of HI gas, and my target, I have 6 moles of HI gas. So how do I go from 2 moles of HI gas to 6 moles of HI gas? How do we turn 2 into 3 when our options are multiplying or dividing? That's right, we multiply by 3, And so if you multiply it by 3, what do you do to the K value? So here I now have 3H2. 1 times 3 is 3I2. 2 times 6 is 3HI. So yeah, K was 54. Now it's going to be 54 to the third power, again, because we're multiplying by 3. And now I can see that, get my pen back, I have in my target 3 moles of I2. I have 3 moles of I2 that I'm looking for. My target, I have 6 moles of HI. In my given, I've got 6 moles of HI. And now I can see that my H2 on the left, my 3H2, my 3H2 on the right are going to cancel. And what else am I left with? In reaction number 1, I've got 1 mole of N2 on the right. And over here, I've got 1 mole of N2 on the right. So I kind of keep track. You know, I want to make sure everything gets circled that I need and everything gets crossed out that I don't need. So now what we're going to do, we're going to apply Hess's law from Chem 101. So when you add 2 reactions, whatever's on the right and the left cancels. And then otherwise, your reactants stay on the left, products stay on the right. So I have 2 NH3 gas plus 3 I2 gas in equilibrium with 1 N2 gas and 6 moles of HI gas. What is our new K value? Well, I mentioned this when I explained or introduced practice exercise 5. If you add 2 reactions, you multiply the K values. So our new K, so K of the target, is just 1 over our K P from reaction 1 times my Kp from reaction 2, parentheses, to the third power. So if you add 2 reactions, you multiply the K values, and I got 1.51 times 10 to the 9th. So make sure you can get that on your calculator. And again, 1.51 times 10 to the 9th, that number is huge, right? Really, really big. So what is favored in this reaction? Products or reactants? We need to think about the fact that we learned when K is really, really big, products are favored. If products are favored, so that means that we have mostly HI and N2 in our beaker. Okay. And that's right. So you always want to double check, add the reactions together and make sure they're correct. And again, the reaction we got when we added them together does indeed match our target reaction. Okay, moving forward. Heterogeneous equilibria. So what does heterogeneous mean? Heterogeneous just means you've got a reaction with more than one phase in that beaker or reaction vessel. So maybe solid and aqueous, solid and liquid, liquid and gas, any combination is possible. How does that affect our K expression? So here I'm looking at an equilibrium between lead-2 chloride, an equilibrium with so this is a solid, an equilibrium with aqueous lead-2 ions and 2 chloride ions. And this is what we see in lab in experiment number 2. When you add HCl and you precipitate out lead-2 chloride, remember if you add it to hot water bath, a lot of that lead-2 chloride will dissolve and become aqueous. So the key, the concentrations of solids and liquids are essentially constant. So you can't talk about the molarity of a solid or the molarity of a liquid, right? They're pure substances. We don't talk about their concentrations changing. So that's the case. That means we're not going to include them in the K expression. So Kc is going to be everything, are products that are aqueous, but we do not include solids. So we end up with Pb2+, which is aqueous, times Cl minus squared. And again, we have a squared because our aqueous chloride here has a coefficient of 2. So heterogeneous equilibria, the only thing different, you do not include solids or liquids. Only include aqueous and gases. Let's look at another problem example. So here we have calcium carbonate in equilibrium with carbon dioxide gas and calcium oxide. So I know it's heterogeneous equilibria because I have different phases, solid, gas, and solid. So a quick diagram of what we're looking at. Calcium oxide in one beaker, calcium carbonate in another beaker. You've got this bell jar with carbon dioxide present. And you can see we're starting in this case with a lot of calcium oxide, less calcium carbonate. And once equilibrium is reached, we have much less calcium oxide and more calcium carbonate. How would we write our K expression? I'm going to give you a minute to write that down. K equals, what does it equal? Again, what we're thinking about, we include gases. We do not include solids. So this, I think, is a really interesting case where your Kp value equals your partial pressure of carbon dioxide. So if I were to give you a Kp value, that would tell you the partial pressure of carbon dioxide. And remember, what law do we need to remember from Chem 101 that has to do with gases? Ideal gas law. Pressure times volume equals moles of gas, which is N, times the gas constant, R, 0.08206 liters times atmospheres divided by mole K. So PV equals NR, and again, that last variable, temperature, T, which is always in Kelvin. So if you're given your partial pressure and a volume and temperature, you could, for example, solve for moles of gas because R is a constant. So again, this is just a Chem 101 reminder, not needed for this slide, but as I've mentioned before, anytime we talk about a concept that I want you to remember from Chem 101, I like to remind you of it so you can kind of go back, look over your notes if necessary, or hopefully just use that brief refresher from lecture. Okay, so this is going to bring us to our next practice exercise 6. It says write the following equilibrium constant expressions. A, I ask you to write down Kc, so remember that means we'll be using units of molarity. B, Kp, so we'll be using units of partial pressure. Heterogeneous equilibria, solid, aqueous, solid. What do we include in the K expression? So the K expression means I'm looking for that products over reactants relationship. Again, we don't include solids. There's a big hint. Kp, partial pressure, so units in atmospheres. Plug in, we include gases, do not include solids. So go ahead, pause the video, write down the answers to A and B, and then click play again, and we'll continue on. Okay, thank you for pausing and working on practice exercise 6. Let's go over it together and make sure you got the right answers. So for A, again, coefficients are important. So Kc equals products, Cr3 plus, no coefficient, so there's no exponent there, divided by Ag plus cubed. And again, this cube comes from this coefficient of 3. We do not include solids in this expression, so this is our final answer. Chromium 3 plus, this should be an exponent. I don't know where that exponent went. Exponent divided by Ag plus ion to the third power. Kp, same idea, but now we'll be talking about partial pressures. So Kc, oops, this should be a P, excuse me. K, make that a P on your notes. Kp is the partial pressure of H2 to the 4th. Again, the coefficient becomes an exponent. Products over reactants divided by partial pressure of H2O to the 4th. Again, from this coefficient. Because our iron is a solid, it is not included downstairs. Because our Fe3O4 is a solid, it's not included upstairs. So practice exercise 6, really just a review of the concept from the previous slide where we talked about heterogeneous equilibria, and the K expressions only include aqueous and gases, do not include solids or liquids. I remember that because I know that I put in either molarity or atmospheres into a K expression, and I can't discuss a solid or a liquid with atmospheres or molarity. So that might help you remember that. Okay, moving forward. Practice exercise 7. Okay, this is the start of our concept of ice boxes. We're going to go over this one example in lecture today, this video lecture today, and then I want you to do future examples from your Mastering Chemistry homework. We will go over ice boxes continued, so the exact same concepts, nothing new. We'll go over it with more practice together in Wednesday's lecture. Ice boxes are a problem-solving technique you'll need to use for chapters 15 and chapters 16, and periodically in chapters 17 and 18. So it's an incredibly important problem-solving technique to use. So we spend a lot of time on it now in chapter 14, so that when we get into our acid-base chapters 15 and 16, you're confident with this problem-solving technique. The way I teach icebox is slightly different than the textbook. So please go off my lecture notes. And again, lecture notes from this video lecture and lecture Wednesday and workshop Thursday. So you're probably asking at this point, what is an icebox? I thought that's what I put cold drinks in. So it's also used for chemistry, and we'll talk about it right now. So practice exercise 7. Consider the reaction, and this might not be a practice exercise in your study guide. I think it might be missing accidentally. So if that's the case, just write it on a blank piece of paper or your lecture notes. Consider the reaction: 2NO2 gas in equilibrium with N2O4 gas at 100 degrees Celsius. Initially, so that I in ice stands for initial. Initially, a reaction vessel contains 0.0200 molar NO2. So again, gases we can talk about in terms of molarity. They've got moles, they've got liters, therefore they have molarity. The reaction is allowed to reach equilibrium, and the concentration of NO2 is 0.0172. So ice, initial I, E is equilibrium. Calculate Kc and Kp. So by looking at the problem, I'm given concentration in terms of molarity. So I'll first calculate Kc, and then I'll use my equation that relates Kc and Kp and do that second. Okay, we're going to write down several important definitions about ice boxes. And again, ice stands for initial. The C stands for change. So ice, we have initial. The C stands for change. And the E stands for equilibrium. ICE, initial, change, equilibrium, icebox. Okay, so I typed out a bunch of these important definitions, so you can pause the video as necessary or write down anything from this slide. So important topics that we need to remember for iceboxes. First of all, when do you use an icebox problem-solving technique? I feel like a lot of students have a hard, you can remember the different problem-solving techniques to use and how to use them, but the tough part is knowing when to use that specific problem-solving technique. So when do we use iceboxes? Well, when you have an initial concentration, right, I, an equilibrium concentration, E, and a K value. So those three criteria: initial concentration, equilibrium concentration, K value. And what happens? You'll always be provided two of the values and asked to solve for the third. So maybe you're given I and E, you're asked to find K. Maybe you're given I and K, you're asked to get E. Maybe you're given E and K, you're asked to solve for I. So again, initial, equilibrium, K, you'll be provided two and asked to find the third. So what are the steps we'll use for an icebox? And this is where I differ from the textbook. the steps that I teach for using iceboxes will apply to every single icebox problem for chapters 14, chapters 15, and chapter 16. In the textbook, it varies a little bit based on the type of problem you have, and that's why it's not my favorite way to teach iceboxes. Again, with the method we'll talk about here on this slide, you'll follow these steps no matter what chapter we're in. So please do your best to work with my method. So number 1, write the equilibrium reaction and icebox. So we're going to go over these steps. I want you to write them down in your notes. We'll then do a practice problem together. Number 1, write down your equation, your equilibrium reaction and your icebox. Number 2, add initial values to the C row that are provided in the problem. Just add initial values to the, what should that be? I row. I for initial. So do not write down C. Sorry, I missed this. Write down I. I for initial. So add initial values to the I row that are provided in the problem. If no initial value is mentioned, that means there's nothing present for that specific reactant and product. Write down the value of 0. And again, we'll go over these steps together on the next slide, applying it to a problem. At this point, I just want you to write down these steps on your lecture notes so we can then follow the steps in the practice problem. Number 3, for the C row, write minus AX for the reactants and plus CX for the products. Make sure to include coefficients A and C from your balanced chemical reaction. So again, if you add a coefficient of 2 in front of the reactants, minus 2x, coefficient of 3 in front of the products, plus 3x, and that is just taking into account the mole ratio from reactants to products. Step 4, for the E row, add I plus C, so I plus C equals E. And then step 5, think, most important part. How do I solve for x? So this is the part that's going to differ. When you think, how do I solve for x? You'll then follow a different path, whether you're in chapter 14 or 15 or 16, and based on the problem that's provided. So number 1, write down your reaction in the icebox. Number 2, add your initial values to the I row that are provided in the problem. If no initial value is mentioned, that means the value is 0. So again, this value is your molarity or your partial pressure in atmospheres. Number 3, for the C row, again, your minus X for the reactants because your reactants are getting used up. They're getting used up to make products. You make more products. That's why it's a plus X for the products. Again, carrying down your coefficients to keep track of your mole ratio. And then for the E row, I plus C equals E. I'm sorry, for the E row, I plus C, again, equals E. And then step 5, think, how do I solve for X? Okay, so make sure you have these notes written down. If you don't, please pause the video and then hit play again, and we'll go on to the next problem and apply these steps. Okay, now practice exercise 7. So this is the practice exercise that I initially introduced before I talked about iceboxes. What I've included are the important numbers. So remember, initially our NO2 molarity was given as 0.02. At equilibrium, our NO2 molarity was given as 0.0172. I asked you to calculate Kc and Kp. So this is the reaction that's provided. I'm emphasizing that coefficient. First step, write down the reaction. There we go. Step 2, reaction and the K expression. So again, our K expression, products of a reaction. So add to the icebox steps, write down the reaction and the K expression. This is going to be helpful. This will be helpful to always write down that expression before you go on. So reaction, K expression. Now we're on to step 2, my icebox. These values should not be here yet. The animation isn't working properly. So we've got our reaction, K expression, icebox. Now we're on step 2. Plug in your initial values. So the initial value that was given as, right here, initial 0.02 molar. The initial value of N2O4 is not mentioned. That tells you it's 0. Now on the next step, our change. Minus 2 because the coefficient. So minus 2x for the reactants. What will it be for the products? Plus, because you're going to use up reactants and make products, so we'll make more of this. Plus x. Again, there's no coefficient here because this coefficient is 1. Equilibrium. I plus c equals e. 0.02 minus 2x is our equilibrium. Over here, 0 plus x. So that ends up just as x. Okay, icebox. Recap. Write your reaction and your K expression and your icebox. Plug in your initial values for the change, minus for the reactants, plus for the products. Carry down the coefficients. E, I plus C equals E. Now, what's the next and most important step? Think, how do I solve for x? Well, this is when you now need to go back to the problem and think what other information is given. Well, look at that. At equilibrium, we're given our NO2 molarity as 0.0172. So again, our NO2 molarity at equilibrium equals 0.0172. That will allow us to solve for x. A couple things to point out. For this icebox, I have it shaded underneath the arrow, the equilibrium arrow, because that's where my minus x plus x, that's where my sign of x changes. And I have columns underneath the reactant and underneath the product. If you had another product, you just have one more column right here. And we'll go over those together on Wednesday. So now, how do I solve for x? We talked about the fact that we're given equilibrium information in the problem. So we're told that our NO2 at equilibrium in the problem equals 0.0172. From our icebox, we know, again, for NO2 at equilibrium, it's 0.02 minus 2x. So if NO2 at equilibrium equals 0.0172, NO2 at equilibrium equals 0.0200 minus 2x, well, I can set these two equal to each other. One equation, one unknown, that's all we need, we can solve for it. So 0.0172 equals 0.02 minus 2x. Solve for x, so algebra, subtract 0.02 from both sides, divide by -2, and we end up with 0.0014. And that would represent the molarity of our N2O4 gas. And let's think about this. X represents our molarity of, X represents our molarity. We're talking about molarity because we're given molarity in the problem. That's why we're looking at Kc first. So X represents the molarity of N2O4 gas at equilibrium. Well, we cannot have a negative molarity, so your X value must be positive. That's just a good little reality check to keep in mind. Okay, so now we have not solved the problem yet because remember we're asked to find Kc. So we know that X equals N2O4 at equilibrium. So how are we going to finish this off? So Kc equals N2O4 at equilibrium, and that's equal to X. And now we need NO2 at equilibrium. And remember, that number was given right here. So I'm going to say X divided by 0.0172. And we solve for X. Let's go ahead and just write that in instead of X. We can add our 0.0014, 0.0014, and what did I miss? Make sure you keep that exponent. So I need to square that. So in my calculator, plug in 0.0014 divided by parentheses 0.0172. And my value of Kc into my calculator gives me 4.7. again, icebox, because we have initial equilibrium, we're asked to find K, reaction, K expression, ice table, plug in initial values, minus x plus x, carrying down your coefficients, I plus c equals E, and we got our Kc value. The very last thing to look at, how do we convert from Kc to Kp? Remember, Kp equals Kc times, and we talked about this in lecture last time, so on Wednesday I believe it was, RT, where R is our gas constant, 0.08206, T is your temperature in Kelvin, to the delta N. So really the main tricky thing we need to think about, what students sometimes forget, what is delta N? Well, it's moles of gaseous products, which is 1. Products, gases are 1, minus our moles of gaseous reactants, which is 2, which equals -1. So go ahead, solve for this. So 4.7 times parentheses 0.08206 times our temperature in Kelvin, which was given in the initial problem as 100 degrees Celsius. That would be 373. And our exponent will be -1. Negative just tells us that there's fewer moles of gases in the products and the reactants. Plug that into your calculator. Pause if necessary. Okay, the Kp value that I got was 0.15. Oops, 0.15. Okay, so we have finished chapter 14 up through the introduction to iceboxes. What I want you to do between watching this lecture, hopefully you're watching this lecture sometime on Monday when our normal lecture is supposed to be, and then Monday night, Tuesday, before you come to class on Wednesday, work on some of your icebox problems in your chapter 14 homework on mastering chemistry. We will go over more of these problems on Wednesday, but I expect you to have watched this lecture and worked on some problems, so it's not the first time I am introducing this. Thank you very much for watching this video lecture, and I will see you all Wednesday.